All right, everyone, welcome back to part two. Um, One of the new concepts that we talked about this week was the idea of momentum. Recall that when we talk about momentum, um, the momentum of an object is just the product of an object's mass and velocity. So you just multiply the two together. Momentum is really important because in collisions, momentum is always conserved. What this means is that even though we might lose energy to things like heat or deformation if two objects hit each other and stick together, the momentum of those two objects will still be conserved after the collision. And so in the next few examples, we're just going to talk about how you can use momentum conservation to learn about what happens when things collide. Um, the results here should feel intuitive because this is what you do see when things interact. So if you imagine these situations as they occur in the problems, you should be able to understand the outcome essentially. So let's start with a relatively simple example. A boy tosses a 1.5 kilogram ball at 5.7 meters per second to another 41 kilogram boy standing on a frozen frictionless lake. And what's the final speed of the second boy after he catches the ball? So the second boy is just standing there, not moving. His initial momentum is zero. Okay, the first boy throws the ball at a speed of 5.7 meters per second. The only initial momentum in the system comes from that ball. So the mass of the ball times the velocity, or the initial velocity, or 1.5 kilograms times 5.7 meters per second squared. The units for momentum are different. In this case, I didn't write down the exact middle step here. 1.5 times 5.7, 8.55. And so the initial momentum is 8.55 kilograms meters per second. It's just mass times velocity. There's no particular units for momentum. Now the final momentum is what we're interested in because we want to know the final speed. The 41 kilogram boy catches the 1.5 kilogram ball. And so the final mass of the two together, 41 plus 1.5, or 42.5 kilograms, the momentum has to be conserved. So the initial momentum has to be equal to the final momentum. If we want to find the velocity, then we just say that the initial momentum is equal to the final momentum. 8.55 kilogram meters per second is equal to the final mass, which is 42.5. I don't know what just happened there. Well, I'll work around it. 42.5, my tablet's being a little strange, times the final velocity. And so we would divide both sides by 42.5. And we find that once the boy catches the ball, he was standing still. His friend throws a 1.5 kilogram ball to him. It's somewhere between half a pound or 3 pounds. I forget whether it's twice or one half. I think that would be about 3 pounds. Um, Regardless, he catches the ball. The boy is standing still. If the lake is frozen and frictionless, when he catches the ball, he's going to start moving. But he's going to start moving quite a bit slower than the ball is traveling because he's quite a bit bigger. And so when he catches the ball, his final velocity after catching the ball, 0.20, we'll just call it 0.20 meters per second. So he starts moving, he just starts moving kind of slow. I'm not sure what happened with the line, you guys. I'm sorry about that. Let's take a look at another example. Okay, where we can talk about at least nearly elastic or elastic collisions. In an elastic collision, you have two things that hit each other and bounce off, right? They don't stick together. In some cases, they may bounce off and travel in the same direction. Some cases, they may bounce off and travel in opposite directions. Okay, the best example of elastic collisions that I can tell you about is the game of pool. If you go and play on a pool table, everything that you do is an elastic collision or nearly elastic collision. The game can be mastered based on a fundamental understanding of momentum and the way that the collisions will occur between the different balls. Another example that we can use is a golf club hitting a golf ball. Okay, so we have a 215 gram head of a golf club, and I left the 215 grams in here because I want to make sure that I point out you have to convert things to kilograms. Don't forget about that. That'll mess you up on those homework problems when they don't need to be. 215 grams, it's doing that. I wonder if I can control Z that. Okay. 215 grams is 0.215 kilograms. And this is the mass of the golf club. We'll just use a C. And it is traveling, the velocity of the club is traveling at 50 meters per second. So this is the initial velocity of the club. The ball has a mass of 49 grams, which is 0.049 kilograms. Okay, and its initial velocity is 0. It's not moving, it's sitting there waiting for the club to hit it. What we want to know is after the club hits the golf ball and sends it off at a particular speed, how fast is the club moving? And so we know the initial momentum in this case is going to come from the club itself. Or 0.215 kilograms times 50 meters per second. That will give us the initial momentum. 0.215 times 50, 10.75 kilogram meters per second. The final momentum is going to come about from the sum of the club and the ball. Now we know the final velocity of the ball. We know the mass of the ball. We want the final velocity of the club. If the initial momentum has to be equal to the final momentum, then we can say that 10.75, the final momentum, the same as the initial. The mass of the ball is 0.049. The velocity of the ball after it's struck is 62 meters per second. The mass of the club, 0.215, and we're looking for that last velocity. Uh-oh. .049 times 6.2 will give you, let's see, 0.049 times 62, 3.038. And then we're going to subtract that from 10.75. That'll get rid of this here. And we'll be left with 0.215 times the velocity we're looking for. So I'm having issues with my tablet today, you guys. I need to figure out what's going on here. 10.75 minus 3.038. 7.712. I don't know why it's doing this. Try that again. 7.712. If we then divide by 0.215 to get the final velocity. I'm sorry, I ran out of space here. I think I might have figured out what part of the problem is. The final velocity is going to be, in this case, 35.87 meters per second. So the golf club continues in the same direction after it strikes the ball, but it slows down because it gives some of its energy essentially to the ball, allowing the ball to move. But regardless, the total momentum of the system is still conserved at the end of the collision, after the collision is over. So let's look at one last example of an inelastic collision. And what I want to do here now is I'm just going to zoom in a little bit. And I think that might help keep me from having issues with the strange writing. So an 87 kilogram skater moving at 5.2 meters per second and a 78 kilogram skater moving at 3.6 meters per second are moving in opposite directions. Okay, this is the most important thing in this entire question. Because momentum is a vector, opposite directions means one is positive and one is negative. We can pick which one's which, but because they're opposite, one has to be in one direction and one has to be in the other direction. And so they're moving towards each other and they collide and they stick together. What's the final speed? To do that, we need to use momentum conservation. Okay, maybe zooming in wasn't the best idea. That might work a little better. Maybe not. Maybe not. Initially, we have two skaters, the first one and the second one. After they collide, they stick together and they become one skater with one single velocity. The initial, or the mass of the first skater is 87. The velocity is 5.2. I'm just going to use the larger velocity as the positive velocity. Okay, so we have an 87 kilogram skater moving at 5.2 meters per second. On the other side is 78 kilogram skater moving at 3.6 meters per second. They're going to hit each other and stick together. Okay. This person, this skater has more momentum, right? Larger mass and a larger velocity or greater velocity, which means that when they stick together, they're probably going to be traveling in that direction, but we can actually figure that out based on the signs as we work this out. You just have to remember the second velocity is going to be negative because they're in opposite directions. The final mass when they stick together is the sum of the two. 78 plus 87 is 165 times their final velocity. (87 times 5.2 will give you 452.4 minus 280.8, and that's still going to be equal to 165 times their final velocity. If we subtract the two and then divide, so let's see, 452.4 minus 280.8, 171.6, and then we divide by 165. And if you divide by 165, you should get 1 point something, 1.04 meters per second. They collide and they stick together, and they're traveling at 1.04 meters per second. Because this velocity is positive, sorry, I did that weird thing again. Because it's positive, it's traveling in the positive direction, the same direction as the guy who had the most momentum, as I pointed out earlier. Another example of an inelastic collision would be something like a car collision. And this is what you see when you see, two cars hit each other. The one that's moving the fastest is going to essentially push the one that's moving the slowest, unless you have a huge discrepancy in mass, like a truck. A truck traveling at a slower speed is going to have much more momentum. And that determines what happens in the crash. When they stick together and they crash together, the object with the larger momentum is going to essentially determine which direction they're going to travel. You have to take into account lots of other things if other things are going on. So let's look at the last part of this, which is how much kinetic energy is lost in this situation. Right? Momentum is always conserved, but kinetic energy is not. In inelastic collisions, when things stick together, kinetic energy can be lost due to heat or deformation. Basically, it's just transferred into another form. For example, in a car collision, right, you generate a lot of heat when the two cars collide, and you deform the cars. And so the energy, the kinetic energy that is in the vehicles before they collide is lost when those things are destroyed or changed. We can determine how much kinetic energy is lost by using what we learned about, or what we learned from the momentum, right? So we know the initial kinetic energy for each one of the skaters, right? And we can add those up and find the total initial kinetic energy. Remember that kinetic energy is a scalar, right? So the direction here does not matter. And even if you plug in a negative value for V, when you square it, it's going to become positive. So we're going to get 1/2 times 87 times 5.2 squared. And just like I was saying, to show you, 1/2 times 78 times negative 3.6 squared. As soon as you square it, it's going to be positive. And if we multiply all of this out, then you get a total initial kinetic energy of 1,681.68 joules. And so this is the energy of each one of the skaters added up together. However, when they stick together, they have a larger mass, but they're moving a lot slower. The final kinetic energy, in this case, does not have to be equal to the initial kinetic energy. In fact, it's going to be very different. 1/2 times the final mass was 165 kilograms, the two stuck together. Their final velocity was only 1.04 squared. Part of that came about too from the fact that they were traveling in opposite directions. If they collided traveling in the same direction, they probably would have sped up just a little bit. And so if we multiply this and find the final kinetic energy to be 89.232 joules. And so you've lost almost 1,600 joules of kinetic energy in the collision. We can actually figure out how much is lost by just subtracting. The initial amount minus the final amount will give you the amount that's lost over the course of the collision. 1681.6868 minus 89.232, or just 23. And the amount of kinetic energy that's lost is 1,592. I'm sorry, let me erase that and fix that too. 92.45 joules. So when you're dealing with objects in motion, you can use energy to determine information about the object's motion. When you're dealing with collisions, you can use momentum and the conservation of momentum to determine what's going to happen in the collisions. Now, there's much more we can do here, especially when you talk about a game of pool, and you can start talking about angles and things like that, but that's kind of beyond the scope of this course. Instead, we're just going to talk about things, traveling in the same direction or opposite directions like you've seen here. If you have any questions this week, please feel free to reach out and email me, and I'll be happy to help. Sometimes just working a few of these problems can help you kind of understand what you're doing, and then they'll all be very easy. Your next test will be next week on Chapter 3. And most of the problems that we've covered in the videos this week and last week will be what are on the test. We're not really going to do any new problems next week, so you may not hear from me until the week after. After your next test, I will provide you all with information about your project for the class. The project that's worth 10% of your grade should be available the week after your next test, which is next week. If you have any questions or if there's anything that I can do to help, please feel free to reach out and contact me. And I will talk to you guys soon.